You clicked because you want to know how BitNet B1.58 runs inside standard DDR4 memory without expensive HBM chips. The real stakes here are whether edge robotics can ever be economically feasible if we must rely on proprietary, high-density memory stacks for every inference task. By the end of this explanation, you will understand exactly how violating fundamental timing rules transforms commodity RAM into a compute substrate capable of running complex language models at a fraction of current costs. The prevailing narrative in hardware engineering suggests that to run modern large language models locally, you must buy expensive high-bandwidth memory. This assumption has locked autonomous robots and edge devices out of the AI revolution because HBM is simply too costly for mass deployment. The CaSA project challenges this dogma by demonstrating a radical alternative, intentionally breaking DDR4 timing constraints to force matrix multiplications directly inside DRAM cells. This is not about improving existing protocols. It is about treating memory violations as an engineering feature rather than a failure mode, effectively turning the physical limitations of standard silicon into computational primitives for inference. To understand how this works, you must first visualize what happens when DDR4 operates outside its specifications. Under normal conditions, DRAM cells store data as electrical charges that leak over time and require constant refreshing to maintain integrity. The memory controller strictly enforces timing rules to ensure these operations happen in perfect synchrony with the processor clock cycles. When engineers violate these constraints on a specialized FPGA platform known as DDR4 bender, they manipulate the physical state of the capacitors within the DRAM array. By deliberately allowing charge sharing between cells during specific access windows, the system can perform arithmetic operations directly where the data resides, rather than shuttling it back and forth to a central processor. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This approach relies heavily on the unique architecture of BitNet B158, which uses ternary weights instead of standard floating-point numbers. The model reduces its parameter precision to just 3 states: +1, -1, or 0. This simplification aligns perfectly with the charge-sharing behavior exploited by the timing violations. When a matrix multiplication is executed within these DRAM cells, the system does not need complex arithmetic logic units for every calculation because the physical properties of the memory array handle the summation automatically through shared electrical potential. The result is that 7 projection layers of the first transformer layer execute entirely inside the memory module itself, bypassing the traditional von Neumann bottleneck where data movement consumes far more energy than computation does. Now consider the scale of this shift in hardware economics. By replacing expensive HBM with standard DDR4 modules, the system achieves a density increase that makes it viable for edge robotics previously deemed too resource-constrained for large language models. The theoretical cost reduction is massive because you are no longer purchasing specialized memory stacks designed exclusively for AI accelerators. Instead, you are leveraging high-density commodity hardware already ubiquitous in consumer electronics and industrial equipment. This architectural pivot allows the inference paradigm to move from requiring expensive silicon manufacturing processes to utilizing existing semiconductor infrastructure through clever software-hardware co-design strategies that exploit physical layer behaviors often ignored by standard operating systems. However, this prototype is not without significant production trade-offs that you must understand before assuming it solves every edge AI problem immediately. The current implementation executes the first transformer layer entirely in memory, but still relies on CPU inference via PyTorch for the remaining 29 layers of the model. This partial execution creates a complex orchestration overhead where PCIe round trips between the FPGA and the processor become the primary bottleneck, negating some of the theoretical speed gains from local computation. The discrete event scheduler managing bus contention adds latency that must be calibrated out before the system can achieve consistent performance across all layers simultaneously. There are also physical challenges inherent to this timing violation technique that require precise calibration on every deployment. Specifically, a phenomenon known as MAJ3 self-pollution occurs due to the double ACT row spread mechanism used during charge-sharing operations. This effect causes unintended data corruption within adjacent memory cells if not carefully managed through complex software algorithms and hardware tuning. The project highlights that while violating timing rules is viable for proof-of-concept demonstrations, maintaining stability in a production environment requires sophisticated error correction mechanisms that are currently difficult to implement at scale without native silicon support designed specifically for these operations from the ground up. The gap between this experimental proof of concept and a fully deployed end-to-end edge solution remains unquantified regarding latency overheads and hardware maturity. While the technique proves that commodity memory can serve as a compute substrate, it currently exists only on an FPGA testbed rather than in native silicon chips designed for commercial deployment. The absence of full model execution means we are still observing how much performance is lost to orchestration delays when shifting between local DRAM computation and external CPU processing. This suggests the angle requires qualification regarding current latency overheads before companies can rely on it for real-time autonomous systems where milliseconds matter significantly more than theoretical throughput numbers. The ultimate insight here is that hardware-software co-design offers a viable path forward even without new semiconductor manufacturing processes, provided we are willing to accept certain operational complexities in exchange for cost and density benefits. By treating timing violations as programmable primitives rather than errors, engineers can unlock capabilities in existing memory architectures that were previously thought impossible through standard protocol compliance alone. This shift represents more than just a performance tweak. It is a fundamental reimagining of how we utilize physical silicon to solve computational problems at the edge without waiting for specialized hardware supply chains to mature or become affordable enough for widespread adoption across the robotics industry. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.